Welcome back to AK Apt Logics. In the previous class, we have discussed about the design and verification of NAND gate in Verilog. Okay. Today in this class, we are going to discuss about design and verification of NAND gate in Verilog. Okay. So without any delay, let's move into the video. So I already told you how to use the EDA Playground in the previous class. So I am not going to discuss that point again. So this is the place where we are going to write the code for our design. So first we need to write the code in between module and end module. So I am going to give module and end module. After module you need to specify the module name. Okay, I'm going to specify it as NAND gate. So today in this class I am going to write the code for NAND gate in NAND gate code in gate level model. Okay, gate level model. So we need to open the parenthesis and close and you need to put the semicolon inside the parenthesis. You need to give what are the inputs and what are the outputs. Okay, for that you need to have a idea about basic NAND gate structure. So if you are going to see the NAND gate, the NAND gate will be like this. See, NAND gate will be visible like this. Okay, it is consist of two inputs. Those are, let us assume that inputs are A and then B, and we are going to have one output which is Y. Okay, so we need to include those things using the keywords input and output, right? Input A comma B and then output Y. Okay, we have given the port list inside the parenthesis. Now after the semicolon till the end module you need to write the logic in your uh, desired abstraction level. So today we are going to discuss about the gate level abstraction, right? So in gate level abstraction you are going to have the keyword or the primitives for each gate. So we are going to use that primitive. It means for NAND gate we have primitive as NAND, and you need to give the instance name. I am going to give it as N0, and you need to open the parenthesis and close it, and need to use the semicolon to end it. So in this uh, parenthesis you need to give the values, all the inputs and all the outputs. Okay, first you need to specify the output followed by all the inputs. Okay, for NAND gate we are having the output as Y and the inputs are A comma B. This is how we are going to write the code for NAND gate in gate level model. Let us develop the TB now. TB will be developed in this area, so I'm going to use module and then end module. TB also will be specified in the both module and end module. We need to give the TB name. Okay, I'm going to give it as NAND gate TB, and you need to use the parenthesis and just close it. We shouldn't give any values inside the parenthesis. Okay, so now in TB there will be no any inputs and outputs. We are having only test cases, so that okay, the inputs in the which are declared in the design module will be becoming regis type of reg in TB. Okay, the inputs are A comma B. So I am going to give the data type reg for the inputs in the test bench. We shouldn't call them as input in the test bench. We should call them as test cases or the test vectors. So output will be assigned with wide data type. So we have assigned both inputs and outputs of design in the TB. Now what we need to do is instantiate the design module inside the design module inside the test bench. So how we are going to instantiate the design module into the test bench means you need to use the module name. The module name of our design is NAND gate, right? NAND underscore gate. After that you need to give the instance name which is N0. It is user defined. You can give any of the name, and then you need to open the parenthesis and then close it, semicolon. So now what you need to do is you need to specify the inputs and outputs which you have written in the port list of the design as it is inside the parenthesis. So I am going to give them as A comma B comma Y. This is one style of writing instantiation. There is another style as well, based on the positioning and based on the naming. There are two styles of instantiating the module. So this is one way of instantiating the module. So we have also instantiated the module. So now we need to give the we need to apply the test cases, input test cases, and we need to observe the output. For that, I am going to take initial block. Why I am going to take initial block means we are required to apply test cases only one time and then observe the output only one time. We are not going to continuously applying the inputs forever, right? So that I am going to use the initial, and I am going to begin and then end. Why? Because in initial we are going to use multiple number of statements. Initially, I am going to give 0 nanoseconds delay. At 0 nanoseconds point of time or the delay, I am going to apply input A and B as 0, input A and B as 0 C. Okay, A equal to 1 tick B 0 means at 0 nanoseconds point of time you are going to apply test case 0 for the A, and also you are going to apply test case 0 for the B input. At 10 nanoseconds of point of 10 nanoseconds point of time you are going to apply A equal to 1 tick B 0 and B is equal to 1 tick B 1. Okay, we are having two inputs, right? So that we are going to have four combinations of input, four combinations, that is 2 power 2, which is 4, 0 0 0 1 1 0 and 1 1. We are going to give those test cases one by one, specifying some delay, by specifying some delay. Okay, see, this is how we are going to give. Okay, this is how you are going to give the test cases, and you are going to give some additional delay. I am going to give some additional delay additionally. I am going to give it 20 nanoseconds. Okay, so what does this means at 0 nanoseconds point of time we need to apply the inputs 0 and 0. Oh, sorry for the interruption, guys. At 0 nanoseconds of point of time we are going to apply A equal to 0 and B equal to 0 after 10 nanoseconds. Okay, or after 10 nanoseconds, or at 10 nanoseconds point of time we are going to apply A equal to 0 and B equal to 1. At 20 nanoseconds point instant we are going to apply B is equal to A is equal to 1, B is equal to 0. At 30 nanoseconds point of time we are going to apply A is equal to 1, B is equal to 1, and then we are going to wait for 20 nanoseconds, and then we are going to stop the simulation using the dollar finish. Okay, this is how we are going to write the code. Till now what we have done is we have given only the test cases, right? We are not going to observe the output. To observe the output you need to use the, either you can use the dollar display after each and every test case. Okay, or you can simply use directly dollar monitor, which is a system task. You need to specify dollar monitor. First I am going to display the time. For the time equal to percentage 0t. Percentage 0t is the format specifier for the time, and I am going to take output, take the I am going to print the input, which is input test case, that is A is equal to percentage b and B is equal to percentage b, percentage 0b, and then corresponding output, that is Y is equal to percentage 0b. This thing I am going to print in the console or the log file. For that you need to give the dollar time for the percentage 0t format specifier, which is used to print the current simulation time. After that you need to give the parameters as A comma B comma Y for the inputs and outputs. Okay, for the inputs and outputs we have given it. So this is how we are going to do. Now let us end the initial block. I think I almost done everything. So this particular line prints the output onto the log file. If you want to uh, if you wanted to observe the waveform, then you need to include the dollar dump um, dollar dump where's and dollar dump. Okay, there will be dollar dump where's and then dollar dump. Two system tasks will be there, we need to include them. Okay, see, these are the two lines which are used to showcase our waveform. Okay, here in the top module name you need to give the module name of tb, that is NAND Gate underscore tb, and you can use any of the vcd file name. Okay, I'm going to give the vcd file name as NAND underscore gate underscore tb. Okay, so dollar dump file is used to dump the file. Dollar dump where's is used to display our variables onto the waveform window. Okay, so this is how we are going to write the test bench. Let us observe the output by running it. Before saving it saving the code, you need to select the tools. That you need to select the first tool which I have discussed already. Save it, and then run it, and then run the code. So there is one error, fifth line, 11th. Okay, what is the error? In the tb, right? In the design we are going to have fifth line, 11th line is error. Good. See, I haven't mentioned comma over here, so that we are going to get an error. So save it, and then again run it. Now you are going to see the output, I think so. Yeah, in the see, we are going to observe the output, right? At 0 nanoseconds point of time, we are going to apply the inputs as a equal to 0 and b equal to 0, and we are going to observe the output as 1, y is equal to 1 at 10 nanoseconds point of time. Okay, at 10 nanoseconds point of time or after 10 nanoseconds. Okay, this particular hashtag 10 says that it is not at 10 nanoseconds point of time, it is after 10 nanoseconds point of time. Okay, at 0 nanoseconds point of time, or it can be able to say like that, after 0 nanoseconds of time we are going to apply a is equal to 0, b is equal to 0, and we are going to observe the corresponding output as y is equal to 1. In the previous video I have been mistaken while discussing about the NOT gate. I have told you that at 10 nanoseconds point of time, no, after 10 nanoseconds of time. Okay, after 10 nanoseconds of time, from 0 after 10 nanoseconds of time, obviously it will be equal to the 10 nanoseconds, right? At the 10 nanoseconds time only you are going to apply the a is equal to 0 and b is equal to 1, and you are going to observe the y is equal to 1, which is output, right? So when you are going to see the third case, it is not like that. After 20 nanoseconds of time, now we are at 10 nanoseconds of time instant. After 20 nanoseconds of time instant, it means after 10 nanoseconds another 20 nanoseconds, it will be become at it will become 30 nanoseconds, right? Now we are at 30 nanoseconds point of time, we are going to apply a is equal to 1, b is equal to 0, and we are going to observe the output as y is equal to 1. Okay, now we are at 30 nanoseconds of time, right? We are going to apply another 30 nanoseconds. Okay, we are going to wait another 30 nanoseconds of time. Now at that time 60 nanoseconds of time, at 60 nanoseconds of time we are going to apply a is equal to 1 and b is equal to 1, and we are going to observe y is equal to 0. If you are going to see the output at if you are going to see the outputs corresponding to the inputs, then we can able to see the truth table of the NAND gate, right? So this particular design code is functionally correct, and it is working as a NAND gate. Okay, this is how we are going to observe the output in the log file. Okay, this design code is correct. Okay, so this is how the code works, but you need to remember, okay, I mistakenly told you in the previous video at 10 nanoseconds point of time, like that. So no, it is not like that. After 10 nanoseconds, okay, after 0 nanoseconds, we are going to apply a is equal to 0, b is equal to 0. After 10 nanoseconds, okay, we are going to apply a is equal to 0, b is equal to 1. Now from 10 nanoseconds, after 20 nanoseconds will be 30 nanoseconds, right? At 30 nanoseconds point of time, we are going to apply a is equal to 1, b is equal to 0. Now we are at 30 nanoseconds. Now the simulation is at 30 nanoseconds. Again, after another 30 nanoseconds, we are going to apply a is equal to 1 and b is equal to 1. It means we are going to apply a is equal to 1 and b is equal to 1 at 60 nanoseconds point of time. Okay. Okay. After from 60 nanoseconds of time, after 20 nanoseconds of time, it means at 80 nanoseconds of time, we are going to stop the simulation. So this is the working of the code. Okay, in the previous video I have told you that uh, I have confused, so that I told you that at 10 nanoseconds of time, at 20 nanoseconds of time, at 30 nanoseconds of time, like that. No, it is not like that. Okay, it is like after 10 nanoseconds of time, after 20 nanoseconds of time, at this current time of instant, after 10 nanoseconds of time. Now we are at 10 nanoseconds of time. Now we are at this point of 10 nanoseconds of time. After 20 nanoseconds of time, it will be 30 nanoseconds, right? Now we are at 30 nanoseconds of time. After, now at 30 nanoseconds of time, after 30 nanoseconds of time will be 60 nanoseconds of time, right? Now we are at 60 nanoseconds of time. After 20 nanoseconds of time will be the 80 nanoseconds of time. Now we are going to stop the program. This is how the code works. Okay, so the delay is most important. Okay, so that I am going to print the current simulation time, right? See, it is got the output as 60, right? Okay, this point you need to remember. Now let us open the waveform. You need to click open EPWave after run. Okay, then save the code and then run. Now we are going to see the waveform for the same NAND code TB. Okay, see, where is the output? Yeah, see, you can see the output. We are having the inputs A and B and the output. This is the waveform. See, after 0 nanoseconds of time, we are going to apply A is equal to A is equal to 0, B is equal to 0. Okay, and we are going to observe the output Y is equal to 1. Okay, Y is equal to 1. From 0, at 0, after 0, we have applied the A is equal to 0, B is equal to 0 and observed the Y is equal to 0. We are waiting for 10 nanoseconds of time, and at 10 nanoseconds of time, we are going to apply again A is equal to 0 and B is equal to 1. Okay, again A is equal to 0 and B is equal to 1, and we are going to observe the output Y is equal to 1. Now we are at 10 nanoseconds of time. From 10 nanoseconds of time, we are going to wait 20 nanoseconds of time. Okay, which is 30 nanoseconds of time, not 20 nanoseconds. Okay, in the previous video what I have told, at 20 nanoseconds point of time, like that I have told you, but it is wrong. Okay, now we are at 10 nanoseconds of time. We are waiting 20 nanoseconds of time, which is 30 nanoseconds of time. At 30 nanoseconds of time, we are going to apply A is equal to 1 and B is equal to 0, and we are going to observe the corresponding output, which is Y is equal to 1. Now we are at 30 nanoseconds of point of time. Now we are at 30 nanoseconds point of time. From 30 nanoseconds of point of time, we are waiting another 30 nanoseconds of time, that is 60, right? At this point of time, we are going to apply A is equal to 1 and B is equal to 1. We are going to observe the transition in the output, that is from 1 to 0, right? So this operation, this is the operation of the NAND gate, right? if you are going to know about the truth table of the NAND gate, then you can able to understand our output is correct in both waveform and also log file. So this is how we are going to see the output. This is all about the NAND gate in NAND gate in gate level model. Okay, thank you.